So in this video, I'd like to go over some of the basics of proton-proton coupling. All right, this is definitely an HL topic, so just keep that in mind when you're going through this. All right, so what proton coupling is in an NMR spectrum? It's the thing that causes signals to get split into either a triplet or a doublet or a quartet. First of all, what causes this? Okay, well first let's go back to a little bit of a basic about the way NMR works. All right, when you're doing NMR, you're taking a sample and you're putting it inside of an incredibly strong magnetic field. All right, so just for perspective on this, okay, so just for perspective, this is what a typical NMR magnet would look like. All right. This thing is like from the floor to the top is probably about 8 feet tall, and typically you're going to see a lot of times like a set of wooden steps beside that, so that if you're not tall enough, you could climb up. And you actually put your sample in the top of it, and it drops down into the middle of this machine right here. All right. The reason that you always have this little part right here with an NMR is that this thing right here is filled with liquid helium in the very middle. Actually, there's what's considered a superconducting coil in the middle of this. All right, and that coil has to be surrounded by liquid helium, which is in the middle of this. And liquid helium boils at a really, really low temperature. So to insulate that, you put an outer layer of liquid nitrogen around that. All right, so every NMR is going to have these are essentially jackets of the center one is liquid helium, the outer one is liquid nitrogen, and this creates just an incredibly strong magnetic field. All right, so you can kind of think of the top of this as being like the north end of a magnet, and the bottom end of it as being the south end of a magnet. And when you're doing the actual experiment, you've got your sample, which is in just a really, really tiny test tube that's sitting in the middle of this. It's floating on actually floating on a little cushion of air. All right, so one thing about some practical aspects of dealing with NMR is that these things generate incredibly strong magnetic fields. All right, and that causes a couple of practical issues. First of all, although a lot of credit cards now have the chips in them, traditionally credit cards have had little magnetic strips on the back. All right, well that the magnetic fields from these NMRs are strong enough that if you were to walk straight up to this and have your wallet in your back pocket, it could very potentially erase those credit cards. So one common practice when dealing with the NMRs is that you take your wallet out before you ever get close to one of these things. All right, so let me pull up another image. All right, so this right here shows a more modern example of an NMR magnet. All right, this one's even bigger. All right, in fact, one this big would probably be overkill for most organic molecules. But if you're someone who's studying things like proteins or some biological molecules, having one of these really, really strong NMR magnets is beneficial. Right? But one thing that you'll notice about this is that there's not a lot of stuff in this room. In fact, whenever you have an NMR, you generally devote an entire room just to that purpose. All right. In fact, when you buy one of these things, you generally have a person on staff whose sole job is to take care of this thing. All right. So again, if you were to be placing a sample in this when you walk in the room, first thing that you're going to do is put your wallet on the counter so that it doesn't get near this. Another thing is you want to make sure that you probably wouldn't want to have your keys in your pocket, because the magnetic field is so strong that if you get close, you're going to feel a little tug from your keys. All right. Last thing about dealing with NMR is if you happen to have a pacemaker, unfortunately, you're probably not going to be able to actually put the sample in there. You could still run the experiment. You would just have to have somebody else physically put that sample in there, because the magnetic field would interact with the pacemaker, which would cause a pretty serious health issue. So before moving on to describe what causes this, I just want to point out a couple of simplifications that they make in the IB with regards for what you're expected to know about couplings. All right. First of all, you're only expected to know that couplings are caused by protons on adjacent carbons. All right, so what I mean by that, so if I draw this couple of carbons in a row, this hydrogen right here is on an adjacent carbon to the hydrogen that this one is on. All right, so these right here would be considered adjacent carbons. And so when they talk about coupling, they're basically talking about the effect that this hydrogen would have on this hydrogen right here. All right, one thing that they don't expect you to know, or would not have you believe, is that hydrogens on the same carbon could couple to each other. All right, that is possible in some cases. In fact, it's a very strong coupling, but you're not expected to know that, nor are you expected to know that this hydrogen right here could couple to a hydrogen which is separated, which is not on an adjacent carbon. All right, so this is the only type of coupling that you're expected to know. Another simplification that they make is that they assume that the size of coupling is always the same. All right, and that's definitely not true. All right, sometime you can have a coupling. So notice that these are both doublets. All right, but the distance between these two peaks is relatively small, and the distance between these two peaks is relatively large. All right, and that's because this right here is being split by it's a stronger coupling, a weaker coupling than the coupling that's causing this splitting right here. All right, but the way it's described, you basically could assume that it would be like saying that every doublet was had the peaks exactly this far apart. All right, so again, let's talk about what causes the splitting. All right, so recall that like when you're doing the experiment, you're placing these molecules in a very, very strong external magnetic field. All right, remember the magnets I just showed? That's what creates this really, really strong magnetic field. All right, and your sample is going to be inside of that machine, and so this molecule, think of it as, it's in the middle of this really strong magnetic field. All right. So one thing that happens to protons when you put them in a very strong magnetic field is that the protons have a little bit of a spin. You might recall that from quantum mechanics or the electron cloud model. But that spin is either going to be aligned with the external magnetic field or against that external magnetic field. And it's actually pretty darn close to being about 50-50. All right, there's only a slight difference in the amount of one versus the other. All right, so what ends up happening is that if a proton has its spin aligned with that magnetic field, it creates a slight magnetic field of its own. All right, and the slight magnetic field that it creates actually adds a little bit to the magnetic field that this thing right here, this neighboring hydrogen, would be experiencing. All right, so if we want to say, well, how much magnetic field would this hydrogen right here feel? Well, it would feel the entire force from the external field, which is caused by the magnet, but it gets a little bit of a boost from this one right here. All right, so in contrast, let's take a look at this molecule right here, but pretend that this hydrogen had its spin aligned against that external magnetic field. All right, so it's opposite of what this one is. All right, well, what that's going to do is it's going to create a small amount of a magnetic field that is opposite of the direction of this one right here. All right, so what this neighboring hydrogen is going to feel is going to be the full strength of this external field minus the amount of magnetic field that this hydrogen right here is creating. All right, so essentially what happens when this hydrogen, all right, is in the spectrometer, when it gives a signal, the molecules that are of this type right here, all right, this hydrogen right here is going to feel a slightly different magnetic field than this hydrogen right here. And so this version of the molecule will create this peak of the signal. All right, but this hydrogen from this version of the molecule would create this peak right here. And so why is it about 50-50? Because about 50% of the molecules would be in this state at any given point in time, and about 50% of them would be in this state right here. All right. So notice we created a doublet by having one neighboring hydrogen. All right. And the amount of peaks that you're going to get is going to be one more than the number of neighbors. All right. Again, this is a little bit oversimplified because in order for that to be true, all of the coupling constants have to be the same. In reality, since they're not the same, what I just told you is not necessarily true. But for this course, that's going to work. All right. So since each hydrogen, as I showed here, each hydrogen's got a 50-50 chance, all right, of being either spin aligned with or spin aligned against that external magnetic field. All right. Well, what if instead of having one hydrogen attached here, we had two hydrogens off this carbon? Well, what's going to end up happening is we're going to have a statistical distribution. All right. So let's here we've got two hydrogens instead of the one hydrogen right here. All right. And I drew 4 different versions. All right. And so there's going to be 4 different possible situations. You could either have both of those hydrogens aligned with the field. You could have both of those hydrogens aligned against the field. You could have this one aligned with and this against, or you could have it reversed, where this one right here was against and this one was with. All right. And if you think about all those permutations, one thing that you'd realize is that there's 2 ways you can get one with and one against. Right. But there's only one way that you can get both with. There's only one way that you can get one against. All right. So what would this hydrogen right here feel? All right. If it were sitting there in that magnetic field. All right. Well, in this case right here, both of these guys would add to the magnetic field. All right. In this case right here, both of these guys would subtract from the magnetic field. But for these 2 versions right here, since these are opposite, they would actually cancel each other out. So this guy would feel essentially only the external magnetic field. All right. And it's because the effects of these guys cancel each other out. All right. Same thing here. All right. So what ends up happening is that the version of the molecule that has both with, all right, is going to be responsible for this peak of that signal. All right. The 2 that are like this would be responsible for the middle. All right. So one thing, if you've seen a triplet before, you'll notice that the center of the triplet is larger. There's actually more area under this part of the peak right here than there are on the sides. All right. And that's because there's 2 separate, there statistically are more molecules that create that center peak because of these 2 things right here than there are from either of the outside. So these 2 which are against would cause that one. All right. So again, you get 3 peaks that are caused because you get 2 neighboring hydrogens. All right. So as far as interpreting, what you need to make sure that you understand is if there's 3 neighboring hydrogens, it's going to be a quartet. If there's 5 neighboring hydrogens, I guess that would be a forget the name for it, but there would be 6 peaks in the spectrum, and so on. So hopefully that will help in the interpretation, and that's it for this video.